Hi everyone, and welcome to my first video on real analysis. We're going to be tackling this theorem on the board in front of me today. The proof is extremely hairy. It's not like terribly long, but there are a lot of little nuances that go into it to make it right. I studied this for my real analysis qualifying exam as a PhD student. And when I was studying it, I thought it was one of the ugliest things I had seen. Uh, and now that I've passed that exam and had some time to reflect on it, I think the proof of this theorem uses a lot of techniques from real analysis that are incredibly useful, and it sort of combines them all into one. So, on the one hand, yes, it might be very ugly in some respects. On the other hand, very useful. So let's see if we can tackle this. First of all, I'll just read what the theorem says. If you have a convergent sequence, x sub n, then the sequence of means, essentially, which I label yn, has to converge to the same limit. So it's really two things there. One, the sequence of means converges, and then perhaps surprisingly, it converges to the same value as the original convergent sequence. I call this the sequence of means because, of course, x1 dot 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 up to xn, if I sum those and then divide by n, I get the mean of those n numbers. And that sequence is built by just doing that for n equals 1, n equals 2, etc. until you keep going to infinity. I could show some examples, but they get kind of ugly because you're doing huge computations. But just pictorially, I suppose, if I were to put, let's say, purple dots down here for xn, so this is x1, x2, x3, x4, etc. And that keeps going and converges to some limit, hopefully. Then the sequence of means, the first term would just be x1 divided by 1. So y1 would coincide with it. Y2 would be the mean of the first two numbers, so just the average of x1 and x2. I'm not going to align these perfectly. I'll just say roughly the average of their y values lands like there. And then for the third term, the average of all three of those might be here. Again, don't worry about the x-axis alignment. I'm just trying not to overlap things too much. And then y4 might be here, y5. And just looking at this, it might not quite look like the purple and the red sequence, the x's and the y's are going to converge to the same limit. Right, if the x's converge to, say, here, maybe it looks like the y's are converging to some higher number. But you can maybe convince yourself that they will converge to the same limit if you remind yourself that, oh yeah, if I go out here far enough, some big value of n on the x-axis, then there's going to be some, massive value, massive index n, and some xn associated to it, and past there, like, xn's not necessarily going to be constant, but if it's converging, it's going to get close to a constant sequence, right? So it looks like a flat line. And the averages, if I went far enough out, the averages are sort of going to be weighted really heavily by these. And so even though, the x1 and x2, etc., might have started up higher, and we're initially keeping the red dots higher than you would expect, eventually, the y's will get dragged down because the x's persist, right? They reach a limit. So that's why xn has to be a convergent sequence for this to hold. Maybe I should rephrase that. It's possible for xn to diverge and for yn to still converge, but at least it's a sufficient condition. If xn converges, then so will yn. Okay, so how might we go about proving something like this? Well, as with any sort of convergence proof, you should start with some arbitrary epsilon. So I'll say let epsilon be some arbitrary positive number. And okay, I'm saying xn is convergent, but I'm not saying what it converges to. So let's just give a name to the limit. So I'll say, and suppose xn, this will be my notation, xn converges to L. And let's just say what that means, right? So we'll just follow our nose for the beginning. Then there exists some index n where, sort of like I was drawing in the picture, for any index past that point, xn minus the limit is, as small as we want, smaller than whatever epsilon we set at the beginning. Great. So that's what it means for xn to converge. It's good to have that written down, but we really want to think about how yn is going to converge. So I'm going to, I know how this proof goes, so I'm going to skip some space. Right? Often in these analysis proofs, you write down what you know, then you try to explore the thing you don't know, and you end up having to go back and edit a bunch of stuff. So I'm just going to leave some space here, and then I'll say, okay, then the quantity I really want to look at is yn minus L in absolute value. My hope is that's less than epsilon for sufficiently large values of n. And I know the definition of yn. I know yn is the mean of the first n entries in the x sequence. So I could write this. And I look at that and I say, okay, how am I going to get that less than epsilon? That seems kind of hard. It's kind of an ugly expression. Maybe your algebra brain just says, well, I can make it a slightly nicer expression if I combine these into a single fraction. So let's just follow that instinct and see what we get. That would be x1, so the numerator is still x1 up to xn. But then this would become like nl over n, right? So I get a minus nl here, and all of this is over n. Okay, still ugly, but maybe getting nicer. The big problem, though, is I still don't know what to do with this, and my only knowledge is about quantities of this form, x sub n minus L. So how can I get those involved? Right? If I don't use the assumption, then I'm going to be stuck. So how do I use this assumption? Well, I could look here. I could say I have n terms of the x sequence, and I have n copies of L. Maybe I could pair up one value of L to each entry in the x sequence. Right? So x1 gets an L, x2 gets an L, up until xn gets an L. So what that looks like, let me erase this highlighting. What that would then look like is, let's also just pull this 1 over n out. N is positive, so it can come outside the absolute value like this. And then I would just have, so I'm saying x1 minus L plus x2 minus L, etc., until I get to xn minus L. That's all within absolute value bars. And so great, I've paired up my terms so that they sort of look more like this. And you might say to yourself, well, they don't look exactly like that. There are a couple things that are wrong, but at least we're getting closer. Right, so maybe we're starting to see some light at the end of the tunnel. Okay, this is where we need to start making some adjustments. This is where the first nuance comes in, as I was saying in the beginning of the video. The first nuance is this less than epsilon criteria only holds for sufficiently large n, right? Only if I go far enough in the x sequence do I start getting terms really close to the limit. So for example, it might not be true that the absolute value of x1 minus L is less than epsilon. It might not be true for 2. Somewhere hiding in here, though, is some, well, that index n that I'm talking about, where beyond that point, it works for, terms past there, for this xn minus l, say. So there are big question marks about what I do with these guys. And then hopefully for terms later in the sequence, I can use my epsilon assumption that we started with. Okay, so let me write a few things to sort of make this look more like what I want it to look like. I'll write this as 1 over n. x1 minus L is still there, x2 minus L, I'll put that in dot dot dots. And then eventually I get to this value of n, right? So I get to, maybe let's go 1 before it, xn minus 1 minus L, and then I get xn minus L. This is the place where past there, all my terms should be less than epsilon in absolute value. So I'll say dot dot dot, and then eventually I get to the last term, x little n minus L. And there we go. One thing you might note is that big N is smaller than little n, which is sort of an annoyance of the notation I'm using. I apologize for that. But it should make sense because we know, just like up here, when we're proving convergence properties, you always, consider little n past some index big N. So maybe I'll add this in here and be like, for all little n bigger than big N, this holds. Okay, so little n is bigger, big N is somewhere in the middle there, and for all these terms, good things happen. Okay, so that's the first little nuance. The second little nuance is one of the most commonly used tricks in real analysis, at least introductory level real analysis. If I have an absolute value of a sum, I can use the triangle inequality. Right? I can split this up into a sum of absolute values, as long as I say, okay, it's less than or equal to that sum. So I could do something like this. For the time being, let's ignore these terms. These are the bad guys that are too early in the sequence to bound by epsilon. So let's leave those alone. I'll put parentheses and I'll keep them over here on the left. I'm terrified I'm going to miss a parenthesis or something. Okay, so I leave that term. And then each of these guys is good. That's past the index I care about, so let's break off each of those individually. So we get absolute value x big N minus L, dot dot dot, absolute value x little n minus L, close the big set of parentheses. Okay, hopefully I didn't miss anything there. I think it looks good. Great, so what I have here is each of these guys is going to be less than epsilon. But still big question marks about this. Okay. So what can we do there? Well, the first observation I'll grant you is that this is a finite number of terms. In fact, since I've sort of, n, big N is fixed, because I know, I've fixed epsilon and there's some specific value of capital N that makes this convergence definition work. N is fixed, so this quantity here should be a constant. Okay, so that's good, but it's not great. What can I do to get around that? Well, let's think for a second. Really focusing on this term, I could possibly say to myself that for, okay, big N is fixed, but for large enough little n, I'm sort of doing 1 over little n times a constant. So if I made little n big enough, 1 over a huge number times a constant should be pretty small, right? So my hope, I'll write this in red, my hope is that I can make this less than epsilon, or or some fraction of epsilon. But how do I write that down, right? So let's go back to the beginning and really focus in on that term. One thing I might choose to write is, well, this is sort of the Archimedean property. So I'll say by the Archimedean property, or yeah, that's basically right. By the Archimedean property, there exists some other value of n, I'll call it n2, such that if I divide by that massive value, potentially massive value of n2, and then let's just copy paste this. Right, so you really see I am thinking about this annoying quantity that we haven't been able to bound yet. I should be able to make that smaller than epsilon. And I should say one other little thing here. Actually, no, yeah, that's fine. Right, I don't need to add anything like, ooh, for all n greater than n2, because, well, first of all, there's no little n floating around here. Again, this term is a constant. I'm making n2 massive enough so that, you know, this constant divided by a massive number is smaller than whatever epsilon I started with. Okay, hopefully that's somewhat convincing. It feels a little maybe out of the blue, but let's run with it. So, and let me relabel some things as well. So I have an n2 floating around. Meant to highlight that. I have an n2 floating around and an n floating around. Just to keep it consistent, let's call it n1. Right? So this is part of what I mean when I say analysts always have to go back and edit what they were working on before. So anywhere there's a capital N down here, I'm going to replace it with n1. N sub 1. Starting to see the ugly details, perhaps, that I referenced at the start. Okay, so we have this, and great. Anytime I have two such indices floating around, I want both of these inequalities to hold. And the only way both of those inequalities are going to hold is if I pick, you know, a large enough value of n, larger than, say, both of those constants. So let's go on the next line and say, whoops, say set n equal to the max of these two big indices, n1 and n2. Okay, and then, okay, I can just scoot this around. I'll be like, okay, for any little n bigger than that, all of my inequalities should hold. And let's see if they do. Okay, now the steps are working out. Everything should be okay. In particular, this term right here is very similar to this term. I just want a capital N2 instead of an N. But I know, let's write this as a note. This implies that, you know, if n is bigger than the maximum of n1 and n2, then it's definitely bigger than n2. But I'm looking at 1 over n and 1 over n2, so if I take reciprocals, I get 1 over n is, the inequality flips, right? I get 1 over n is less than or equal to 1 over n2. So I could immediately throw that down here. Let me just copy paste this so I don't have to write it all again. I can basically safely replace 1 over n with 1 over big N2. And that's good news, right? Because now I have, this is 1 over big N2 times the quantity I care about, Yeah, exactly the quantity I care about. With one small little thing that I might have to handle. Plus 1 over n. So I'm just distributing the 1 over n2 now. I'll distribute it to all these little terms on the right. 1 over n2 times the last one. Okay, I think that looks good, except let's be ultra careful. I forgot to replace that with an n1. So good job if you caught that. I missed it, but that should have been an n1. And now, that matches up with that, which is good. Okay, so let's write what we have. We know by assumption, right here, this term is less than epsilon. And we also have by assumption that each of these terms, not including the 1 over n2, is also less than epsilon. And I think I want to do something here. Yeah, let me make one other small edit. Apologies, there are many little things to care about here. I'm going to make these just normal n's. You'll see why I'm doing that in a second. And it's still sort of true enough. I've probably messed something up slightly. I'll go back and edit a little bit, perhaps. So that can stay. That can stay. Yeah, this should be true. I'll just scoot this line up. That this is less than or equal to that. Okay, so corrections made. This looks fine now, right? I need the less than or equal to because 1 over n is less than or equal to 1 over big N2. Technically, the rest of it is equal to what it was before, so it's, yeah, less than or equal to the line above it. And I would have, at this point, this is less than epsilon, this less than epsilon, and this less than epsilon. Okay, so typically what we want to do in analysis is get it all less than one single epsilon. So let's see if I can manage that. Again, this is not poor planning on my part. I'm just trying to show you how these proofs go in real time. I could have started by saying, ooh, it'll be nice if I make these epsilon over 2 instead of epsilon, but you would have been like, why are you doing that? That seems like it's coming out of nowhere. The reason is because, yeah, I sort of have like two important chunks. If I can make one of them less than epsilon over 2 and the other as well, then in total they'll be less than epsilon. So once we have that, I can write this next line. I can say, okay, this is less than epsilon over 2 plus, right, so that's just for this term. For the rest of the terms, how many things do I have here? Well, it starts at, or it ends at index little n. It started at index little, or big N1. So it's little n minus big N1 plus 1. That's how many terms are there. Take a second to think about that if you need to. This is n minus n1 plus 1 terms. And they each have like a 1 over n in front of them. So what we should get is, okay, 1 over n, sort of factoring it out of all of those terms, times I have n minus n1 plus 1 copies, and each of those is less than epsilon over 2. Maybe you're seeing why, even more why I thought this was ugly when I first solved it. Maybe there's a nicer solution, I don't know. But Okay, looking at this, how do I get an epsilon out of this, or a less than epsilon out of this? Well, we're in the home stretch. It's not too bad. This becomes epsilon over 2. I'll keep that. And then this is n minus n1 plus 1 over n times epsilon over 2. It turns out this quantity is less than 1. You can kind of believe that, or I guess I should say less than or equal to 1. You can believe that because, let me just write something down. So that's the claim. That's, of course, equal to epsilon. So if what I've written is true, then we've finished our proof. So I'll just write over here as a note. This is because little n minus big N1 plus 1 over n is less than or equal to 1. And that's true because, well, you can just kind of fiddle with the inequality, right? This is equivalent to multiply by n on both sides. Now I have a little n on both sides. I can just subtract that from both sides. Maybe I take the negative n1 and add it over to the right, and that becomes 1 is less than or equal to n1, or written more intuitively, big N1 is bigger than 1. That's a true fact, right? Big N1 is a natural number. It's either 1 or bigger. So this true claim is equivalent through that chain of reasoning to this claim. Therefore, I can replace, that constant times epsilon over 2 with just epsilon over 2, as long as I include the less than or equal to symbol. And yeah, that is it. We have successfully shown that for all indices bigger than both of the fixed indices I started with, the distance between the average of the x series and the limit of the x series is epsilon, meaning yn converges to L as well. So let me just write that down as our conclusion. Oops. Hence, yn converges to L. Which is what we wanted to show. Right? If xn is a convergent sequence, then the sequence of averages converges to the same limit. I hope that all made sense. It's definitely a trial to get there. There's some hurdles to leap on the way to a correct proof, but I hope you learned some useful tricks along the way, and thanks for watching.